Now we make use of interaction picture method to construct a time-dependent perturbation theory. We are approaching our goal almost. We have derived the fact in the interaction picture, Schrödinger equation fits into the form where H0 does not appear in the differential equation. And Vi is the interaction picture potential, that is the Schrödinger picture potential sandwiched by this time evolution operator with respect to the H0. And if we define the state cat in the interaction picture at time t to be the product of this time evolution operator in the interaction picture acting on the interaction picture wave function at t equals 0, then the Schrödinger equation reduced into this form. And actually there is no time dependence in the wave function at t equals 0. We can remove this and this equation shrinks into the form. We would like to solve this equation, find the time evolution operator u, and it can be done by using perturbation theory because the left hand side is u and right hand side is u multiplied by v. Okay, note that this v and u may not commute, and suppose v equals 0, then what happens? The ui, time derivative of ui is just 0. That means the ui becomes a constant, and in order to have the same value at t equals 0, that constant must be 1. So we have our constraint that if potential is 0, then the ui that is exactly 1. This shows that ui can be expressed as an expansion in powers of v, and leading order contribution is just 1, and next order is a v and v squared and so on. If v is a very small number, then we can make a power series expansion, and we are allowed to construct a perturbation theory order by order. All right. I can rewrite this ui in power series of v, where the superscript means the power that is the order v to the nth power. All right, and as we have already discussed, the zeroth order component is exactly 1. It is null. And we have another constraint that if we set t equals initial value t0, what's happening is it is also 1. Because there is no time evolution, it must be the same as the initial state, t equals t0. So in that case, u t0 is exactly 1. And we already know that zeroth order component is 1. That means to all orders in v, t0 is 0. Right? So for all n that is greater than 0, everything is 0. So we have this kind of constraint, so initial conditions. Let us substitute this series expansion to our original equation of motion. Right? We observe that ui has some power. Series. And I have additional v on the right hand side. So the two powers are different by the single power in v. So if we substitute this series expansion, I can use a dummy variable n. I just copy this one. And on the right hand side, I have used a different dummy indices that are m. And when n equals 0, this is zeroth order, and there is no such term appears on the right hand side. Okay? That means the time derivative of zeroth order is a 0, and we have constant value for the zeroth order value, and our constraint is that at zeroth order, if v equals 0, the operator must be 1, So that's the reason why we had 0, so the solution is 1. And from next order, I can make use of previous result to obtain the next order result. So this is a time-dependent perturbation theory. This one shows that I have power of m, and I have power of n, and I have one more power. So m, order m plus 1 is the same as n. So this is the constraint. So, alright. So when I put n equals 0, I had this one and this solution. And for all powers of n, nth order derivative is, I multiply this inverse, minus I over h bar, vi, and one less power of u. Okay, so I got this solution at n equals 0. So I put this value in here, and to get the order 1 value, and solve the differential equation, and substitute that one in here to get the order 2, and solve the differential equation, substitute it in here, get order 3, and this one can be done recursively. So let us solve the equation. The first solution was 1, and at first order I have differential equation, and I substitute this value in here. So this is actually function of time. What I want to do is find out the value for order n, order 1, and its initial value was what? 0. So there is no contribution here. So what I have to do is just integrate, find out that integral from t0 to t. Time dependence appears only in the vi, right? In order to get the order 2 contribution, I have the order 1 contribution to the right hand side, and these are t, and this is t comma t0, right? So this is t comma t0. So if I want to solve this, I use the initial value, that is 0, and then take the integral. If I take the integral, what I get is I have this vector, and I substitute this value in here. So I have square of this over vector, right? This integral is written here, and if I substitute this value here, then I have square of this over vector minus I over h bar, and the first integral is from t0 to t, and I use the t2 because I want to identify this to be the same. So t2 integral outside, and I have to use this one. If this is t2, this is t2, integral is from t0 to t2, right? t0 to t2. It is not to t. It is not t, but t2. So this is the answer. If I do this computation repeatedly for all n, which is greater than 0, I have this over factor n times, and then the first integral, actually this is the last integral, from t0 to t, and then t0 to t2, and then t0 to 2, okay, t2. t2 was the last one. So the last one, this is the same as 2. If it were n, then I should have tn, right? tn and tn minus 1, n minus 2, and so on. And this one ends up with t2, not t1. Alright? So the integral is, this is n minus 1 integrals, and there's one more integral. So I have n integrals. But the range of integration is not fixed to be t, but different. They are ordered, right? So we will, in the next page, we would like to simplify this kind of complicated multi-dimensional integral in a simplified form. That is called time-ordered product.